Hello, everyone. My name is Joseph Carlstein, and I'll be presenting on managing engagement on online discussion platforms. I'm a fourth-year PhD student at Wharton, and this is joint work with Gad Elon and Yonatan Gur. So even before COVID led us to remote work, more and more firms used online discussion forums to make decisions and resolve conflicts. So in this age, it's crucial to be able to appropriately utilize these forums. The main questions we want to understand in this talk are, what are the key engagement drivers in online discussions? And how can we leverage these drivers to improve the operations and performance of such discussion platforms? We will show both empirical and theoretical results on what strategies the platforms should use to create, quote, better discussions. So to find out what makes these discussions better, stay tuned. So let's first draw a distinction between different types of online discussion platforms. We distinguish between external and internal platforms in that external platforms are open to anyone, whereas internal platforms are limited to a select group of invited people, such as Slack or Discord. And there can also be very different objectives from the perspective of the online platform. In this talk, we're focused on trying to maximize discussion engagement. But in other scenarios, the platform could be trying to get people to reach the truth. It could be trying to get people to agree, even if they end up agreeing on an answer that isn't necessarily correct. It could be trying to stir up a spirited discussion where lots of different opinions are raised, but there isn't ultimately a consensus. And a common theme for research on this topic in the past has been studying answer level features that drive engagement, such as scores, likes, dislikes, number of replies, or in other words, looking for answers that have driven engagement and then determining what specific feature these answers have, which in turn end up spurring discussion. But our goals are a little different. Rather than focusing on answer level discussion drivers, our main goal is to both empirically and theoretically investigate how discussion level features can drive engagement and how to leverage these drivers to improve the operation of such discussion platforms, such as improving the performance of recommendations. The discussion level feature that we study in depth here is entropy, which measures how balanced the discussion is. We'll give a more specific definition for entropy later on, but first, we'll empirically show that in addition to the standard answer level drivers, entropy drives discussion engagement beyond what the answer level drivers capture. Then we consider the question of how the discussion platform can leverage entropy in recommending which answers to feature throughout the discussion. We'll model this as a dynamic program and describe the optimal solution. But since the optimal solution is computationally complex, we'll introduce an alternate practical heuristic for the platform to use and analyze how close this alternate heuristic is to optimality. And finally, we'll show the analytical results proving the optimality of one of these heuristics under some certain constraints or near optimality under all others. And these results will be confirmed by a simulation based off the platform data. So the relevant literature for this topic can be broadly divided into an empirical and a theoretical category. On the empirical side, there's a slew of recent research in optimizing online platforms using field studies, a topic that has become all the more relevant in the last year and a half, be it recommender systems, online shopping, online learning, and so forth. However, one of the distinguishing characteristics that we employ is using a look-ahead model over a time horizon divided into multiple periods, a key tactic in Rios et al., the goal of which is to maximize matches on an online dating platform. Another key characteristic of our model is specifically taking into account the ordering of answers on the platform, a tactic that has been studied in depth for ordering products and advertisements on platforms like Expedia and Amazon to maximize revenue and consumer welfare, like Ursu 2018. There's a rich vein of literature that specifically explores the answer level features which drive engagement on a variety of platforms. Many of these concern Twitter, such as looking at what factors lead a tweet to go viral and how to predict the cascade size of a tweet or retweet. Another interesting answer level example is the field study in Budak et al., which shows how when the Guardian's news website changed their commenting platform from non-threaded to single level threaded, the number of people commenting a second time increased. And this gets deeper into the heart of specifically platform management and how platforms can be structured to maximize engagement. Now, on the theoretical side, and getting deeper into discussion level management rather than answer level management, in Goal et al., we see how information can travel in two ways through a network: broadcasting, where one person with a wide mouthpiece gets through to a large population, or the opposite, diffusion, where through multiple generations and people passing on information, it seeps its way through an information network. While describing entropy as a feature of discussions is a relatively new idea, there has been some recent work in characterizing entropy in different contexts from ours, such as characterizing Shannon entropy under learning uncertainty, or the relationship between how much sharing a piece of information contributes to a reduction in uncertainty. Now, our data comes from an internal platform called Ment. The platform caters to small to mid-sized group discussions. All discussion participants know each other, and the platform tries to actively guide discussion to create the most engaging discussion possible. To do this, the platform numerically scores responses based on participant reactions and then utilizes these scores to decide which responses to feature. So given a question, as we see in the answer example shown below, upon arriving to the platform, participants have a couple of choices. They have the opportunity to write an answer to the question at hand. In this case, there are 5 different answers, 2 of which the platform has decided to feature and 3 of which are hidden, which the participants will have to actively scroll to see. The literature would suggest that an answer being in a more prominent position will lead more people to interact with it, an assertion which we'll soon empirically verify. Furthermore, we can clearly see how many people upvoted or downvoted each answer, and we see how many people saw each answer. And should a participant choose to reply to an already posted answer or any level of subcomment, they have to indicate whether they agree or disagree with what they're writing in response to in order to guide the discussion along and quantify the direction of the discussion. So based on this data, the platform scores each answer and ranks the different answers to assist the participants. This is how the platform guides the discussion, and this leads to the crux of the matter. For the platform to maximize engagement, what should the strategy for positioning the answers for everyone to see? Currently, Ment's strategy is to place the highest scoring answer first, but is this the optimal strategy? So now that we know how a discussion progresses, we want to gain an in-depth understanding of how specific answers and subcomments are scored. The firm uses a Bayesian recursive algorithm based on the different actions that each participant can take. They can give a quick upvote or downvote. They can give a response where they agree or disagree, or they can just do nothing at all. And not surprisingly, a vote counts much less than a response counts. Scores are also scaled and standardized relative to each other to prevent scores from growing without bound. So to give a sense of what the scores look like over time from an actual discussion on Ment, in the first half hour, with each color representing an answer to the original question, green is the highest scoring answer. Then for the next hour or so, brown is the highest. Then red takes over. But we see brown and red converging as the discussion peters out. We also note that generally, the fluctuations in individual scores get smaller as time goes on, and this can be attributed to the fact that one interaction with an answer that's already had many interactions will have less of an impact on the score than one interaction with an answer that's had very few interactions. So in other words, interactions early on are more influential on the score than later interactions. Now, to improve upon our model, we first want to introduce the key discussion level characteristic of discussion entropy. In its most general form, we'll define entropy as a weighted sum of all the absolute differences between the scores of every pair of answers during a discussion. So in other words, high entropy means that a discussion is imbalanced and there is a clear winner, while low entropy means that a discussion is more balanced and there is a clear competition for being the best. So entropy is a proxy for the balance of a discussion. You may ask whether this is important, and we'll soon show that it is. So for our purposes, we'll provide 3 different definitions of entropy that we'll test out. The differences between these definitions are solely in the weights W sub Ti and W sub Tj. The simplest definition is to just look at the difference between the top 2 scoring answers and have the weights on all other pairs as 0. And conversely, we could weight the difference between each pair of scores equally, or as a happy medium between the previous 2, to put some weight on each pair, but progressively more weight on the higher scoring answers and less weight on lower scoring answers, in line with the effort it takes to see lower scoring answers. Now, going back to the sample graph from a slide back, using the first definition of entropy, where we only consider the top 2, we would say that in the first half hour, we have a pretty unbalanced high entropy discussion, since as we can see, the green first place score is a lot higher than the blue second place score. But if you look to a time of about 1.7 hours, you see that it's a pretty well-balanced discussion where the scores of brown and blue are really close together with a relatively low entropy score. So to show how these features drive engagement, take the following logic regression. Like on the graph in the previous slide, the time frame of a discussion is broken up into several time periods, and our goal is to predict the probability of engagement on an answer I in time period t. In addition to a constant of regression, we have three other regressors: the position which answer I is in the discussion at the previous time period t-1, the score of answer I at time period t-1, the entropy of discussion at time period t-1, and several other controls. Now we run four regressions, the first three each applying a different definition of entropy. Top two scores only, uniform weights, and higher weight for higher scoring answers respectively. And the fourth as a control without any entropy. This will allow us to see the extent of the impact of entropy. So first, we break down the position regressor into two dummy variables, one for an answer being in first place and another for an answer being in second place. And we see that they're both positive and highly statistically significant. So at the present, Ment's policy for positioning answers is to put the highest score answer in first place, the most prominent position. And it's important to recall that a discussion participant can't see every post at once when they load the discussion. They have to scroll through to see the lower rank post, which takes some effort on the part of the participants. So the fact that this result is statistically significant shows just how important the platform's decision regarding the positioning of answers is. Now, we note the significance of the coefficient on answer score, and finally, the statistical significance of entropy in each of the first three regressions. So let's compare the regressions with entropy to the control. We would assume that the control would perform the worst. And so when comparing the mean square error of the regression with the top two entropy to the control, the difference in mean square error is strongly statistically significant. And similarly, the mean square error comparison for the weighted higher weights for higher scoring answers compared to the control, the mean square error difference is also strongly statistically significant. And similarly, the likelihood ratio tests comparing these are highly statistically significant as well. And finally, the Akaike information criterion for the control is significantly higher as well. The equal weights definition of entropy does not quite show significant evidence of an improvement over the control, but the results from the top two entropy and the higher weight for higher scores entropy strongly suggests the importance of adding in a coefficient capturing the entropy of the discussion. So now that we have established the presence of both answer level drivers and discussion level drivers of engagement, we move on to constructing the dynamic program that'll appropriately take this into account. So to model the dynamic program, we start by defining the state and action at a given time. For now, we only consider the scenario where there are two answers, answers A and B, and without loss of generality, answer A is the highest scoring answer. Each answer has a score, which constitutes the state, and for simplicity and practicality, the action undertaken by the platform entails one very specific thing: which answer to feature first. So the platform only has one decision to make. It can place the highest scoring answer in the most prominent first position and the second highest scoring answer in second position for an action of 1, 2, or it can reverse the order and place the second highest scoring answer in the top position and the highest scoring answer in the second position for an action of 2, 1. Then a participant comes along. So in a period, the participant can choose to engage with exactly one of either answer, or they can choose to engage with both answers, or they can engage with neither answer. We assume the user's decision whether to engage with each answer occurs independently. So for each answer, the participant makes their decision. They can choose not to engage, or they can choose to engage. And if they choose to engage, the score of that answer changes, thus changing the state moving forward into the next period. So now that we've defined the actions and state transitions, we can formally define the dynamic program. We've recursively defined the optimal value function as the cumulative probability of engagement in both answers A and B for the optimal action in each period, conditioning on the history, with the optimal value function in the final period, it's big T, defined as the single period optimum under the optimal action profile. In calculating the probabilities used in the dynamic program are based on a two-step nested logic model where the user decides whether or not to interact with each answer with a given probability. And then, given that there is an interaction, the user decides whether their interaction will be positive or negative. So to get a sense of when either action is optimal, starting with just a single period problem, let's take a look at some of the theoretical simulations of the dynamic program. Since discussion entropy and average score are both functions of the scores of both answers, we can compactly represent the state space by mapping the scores of both answers to average discussion score and discussion entropy. We consider the entire possible state space of standardized scores for the given constants as defined in the regression. So in the first graph, where we have rho, the coefficient on entropy equal to 1.2, we find that for most states, shown in red, it's optimal to put the highest score first, while those in blue are states where it's optimal to put the second highest score first. But in the second graph, where we have rho, the coefficient on entropy equal to negative 0.2, and all other constants the same, we see quite a different picture. Suddenly now there are a lot more states where it's optimal to put the second highest score first. We still note, however, that the boundary dividing the state space between the optimal action is still linear and tractable as long as we're in the single period state. So the key takeaway here is that in the presence of entropy, it's not always optimal to show the highest score first. And we see similar behavior as we move into the multi-period problems, but the boundary between the optimal actions grows a lot more complex. So there are two policies for positioning the answers, placing the highest score first and an entropy-driven policy. The highest score first policy just places answers in the order of their scores. It's the most obvious, and it's the policy that's currently used. However, it's not optimal. And conversely, the entropy-driven policy employs discussion entropy, which maximizes the single period objective and will soon show that it's close to optimal for multi-period horizons. The entropy-driven policy itself can be defined quite succinctly by the following equation. Under this condition, we take the standard action of highest scoring answer in first place, second highest in second place, and otherwise, we take the reverse action. So we want to state two results that characterize the entropy-driven policy as a policy that isn't nearly as complex as the optimal solution, yet is very close to the optimal solution in performance. So first, we have the following analytical result, establishing the optimality of the entropy-driven policy under certain conditions. So given a known set of parameters, including epsilon, which is defined as the bound on the 2 norm between the states over adjacent periods and any starting state, for a t period long discussion, there exists a threshold epsilon naught such that for any epsilon less than epsilon naught, the performance of the entropy-driven policy is equal to the optimal performance. And this is a pretty powerful result because it says that for any starting state evolving over an entire t period long discussion, we can say that the entropy-driven policy is just as good as the optimal solution as long as epsilon, the change in the scores each period after an interaction, is small enough. So the next result is similar and establishes the near optimality of the entropy-driven policy under all other conditions. So it provides a bound that is linear with respect to epsilon on the difference between the optimal solution and the entropy-driven policy. So to sum up, the first theorem stipulates the conditions where the entropy-driven policy is optimal, and the second theorem proves the near optimality of the entropy-driven policy under all other conditions. So we've already seen some simulation results for a theoretical single period problem, but now we'll simulate several multi-period, multi-answer discussions 1,000 times over an expanded time horizon using the estimated parameters for 3 different teams on Ment. Each team has a different group of participants, different motivations and goals, and a different personality, which means that different defining parameters. So it's not appropriate to use the parameters of one team to simulate a discussion for another team. For each discussion, we simulate in parallel the positioning of answers using the highest score first policy and the entropy-driven policy. And at the end of each discussion, we calculate the engagement under each policy. Then for each discussion, we calculate the percent increase in engagement under the entropy-driven policy with the highest score first policy as a baseline. And then for all these simulations, for the three teams, we display our results in a box plot. We see that there's always an increase in engagement under the entropy-driven policy. And for the team where entropy in the discussion is much more prevalent, there's a much stronger reaction to the entropy-driven policy. There can be a more than 50% increase in engagement under the entropy-driven policy. So to sum up, we first introduced the concept of discussion entropy, a discussion level feature rather than an answer level feature. We showed that entropy is indeed a driver of engagement in a discussion. And then we developed a heuristic, the entropy-driven policy, that leverages entropy to enable the platform to make decisions about how to position answers to maximize engagement. And this policy is much simpler and less computationally complex than the optimal solution, yet it performs almost as well as the optimal solution does and is equivalent to the optimal solution in certain cases. And our simulations based on real-time data show that the entropy-driven policy can have a major impact on increasing the number of engagements in a discussion, with a higher potential for increased engagement in teams where entropy is a more prevalent discussion characteristic. There are many ways to move forward in both the empirical and theoretical realms. Our goals are to further establish either optimality or near optimality of the entropy-driven policy under more broad conditions, such as bounded variance and non-uniform distributions of the initial state or non-uniform distributions of epsilon. We'd also like to expand the state space to the point where we can actually classify entire action trajectories. And finally, we'd like to implement the heuristic on a real-time field study to verify that its actual performance in a real-time live discussion lives up to its theoretical and simulated performance. And that's it. I appreciate you listening. I look forward to answering any questions. Thank you.